Hello everyone and welcome to my channel. My name is Professor and your friendly professor. I've been teaching physics and math for the past 40 years in various universities in the United States and abroad. In this video I want you to learn about using the Fourier transform in everyday applications for engineering or physics students. Thank you. Hey there. Today I want to discuss about Fourier series and their applications in engineering, physics, business, different fields. That's a very serious topic and it's about applied math. And I'm going to make it very simple and very clear. I'm going to go over very quickly about the goals, the necessity, what are these, how they work, where we can get the prerequisites, the results, and several tricks and an example. So the framework we talk about in discussions about Fourier series is upfront functions, signals, measurements, data, analysis, graphics, anything has a time series. Second hand, you can apply the data you obtain from Fourier series in modeling, explaining data, analyzing, evaluating, and functions and signal, that's a main tool in Fourier series. What is the goal of Fourier series? What's the importance of Fourier series? Why do we invent it and why do we use it? The main thing about them is we can express any complicated function, no matter how busy it is, how unwritable it is, in a very simple way using very simple functions, elementary functions everybody knows, with very simple properties. So it's like decomposing complicated beasts in very simple elements like x, powers of x, trigonometric functions or exponentials, something very easy to work with. That looks like a dream and it's possible. As I said, we can choose, the great miracle about this is we can choose what functions to use. We can choose to decompose that complicated function in powers of x, and what you get is called Taylor series. You probably use it and remember about it. Or you can use trigonometric functions, periodic functions like sine, cosine, and what you get is Fourier series. You can use exponentials, also very simple functions, and you obtain the complex Fourier series and so on. You can go even to more complicated examples, very sophisticated polynomials. They are called orthogonal polynomials or even orthogonal system of functions. So you can extend the knowledge as much as you need it. But today we are going to talk to a very simple example, trigonometric functions, a very original Fourier series. What are the byproducts of using Fourier series? A very important thing is you may not even know your function, you may not even write it down. You know about its existence, you know how to obtain it, and you don't need to write it or express it. You just calculate its Fourier series and you have it represented in a very simple, readable way. For example, you have a differential equation, you have to solve and you don't know how to solve. There is no analytic exact solution. It's no solution to write like compact form in terms of elementary functions, but you can plug into that equation a Fourier series and then the result, your solution, will come up as a Fourier series. So in principle, universal method. Another byproduct is data analysis, signal analysis. So given a set of data, a time series, or any sequence of data, applying Fourier series procedure, you can identify features, recognize patterns, find resonances, modes, important modes of vibration, oscillation, different features of the signal, which you cannot see otherwise. There is a price to pay for the Fourier series. As you can see, it's a very good tool, but the price to pay is you have to deal with infinite sums. We know this under the name of series. You have to deal with series. We cannot write by hand or in a computer an infinite number of terms, but we can truncate, approximate, and we have theorems that tells us that if you would go to infinity with this series, then you have the exact result and so on. So that's one price to pay. We have to deal with problem like convergency, like estimation, truncation of infinite series. Sometimes these series converge slow, sometimes fast, so that's also a price to pay. You have to decide what type of series you want to use. So let's go into Fourier series. I need three prerequisites. I need to remind you three prerequisites. Finite set. What is a finite set? A finite set is a set having a finite number of elements. You can count them and you stop at some point. That's finite. 10, a billion, 10 to the power 26, but finite. It doesn't go to infinity. Finite number of elements. Second prerequisite, bounded real interval. Remember the real axis? You can choose 2 points on it, x1, x2. All the real points between x1, x2 is an interval. You have to have the limits, finite limits, x1, x2. This is a bounded interval. As opposed to unbounded, means the interval extended all the way to infinity, minus infinity, plus infinity, or both. In Fourier series, we work only with bounded intervals. And then I want to remind you the third prerequisite, continuous functions. So functions, y equal f of x. A continuous function is a function you can draw without taking the pen from the paper. It's not interrupted, it's not broken. You just draw it continuously, smoothly. That's a continuous function. There is, of course, a mathematical definition of continuity. Loosely describing it is you pick a point on the real axis x and the value of the function for that x, f of x, y. Then you approach this chosen x in any way you want along the real axis, from the left, from the right, slower, faster, using just odd numbers, even numbers, fractions, you name it. You approach this point you choose on x in any way. And for each such approach, each such procedure to join x, you calculate the corresponding value of the function, f of those x's. If the sequence of the value of the function converges, approaches to a given point, which is a value of the function at that point, your function is continuous at that point. So the idea is no matter how you approach it, you get to the value of the function. That's continuity. And these are the prerequisites we need to know. Next step is what is essential about the Fourier series. 3 things. First, the function which you want to expand in Fourier series, this f of x we are talking about, should be defined only on a bounded interval. From a to b, from x1 to x2, from minus p to p. For Fourier series, the interval must be bounded. It's essential. Later on, if you want to go unbounded, the whole real axis or half of the axis, we are using another tool, Fourier integral, and we'll talk about this later on in another session. Well, your interval can be closed or open closed. In any way, it doesn't matter. It's not important. So the ends of the interval can be contained or not in the domain of definition. This is not essential. And the third essential thing about Fourier series is the function on this interval should be continuous. Continuous on this domain of definition, or it may have just a finite set of points of discontinuity. It's allowed. So your function can be perfect, continuous, not broken, or it may be broken but only in a finite number of points. The number of discontinuities must be finite, not infinite. And at each such discontinuity, the jump of the function, the discontinuity itself, how much function jumps, must be finite too. So we are not allowed to have infinite number of discontinuities or infinite jump of the function, like for example 1 over x has at 0, or tangent of x has at pi over 2. The function may be broken, but move in within finite range, bounded, and the interval bounded. In other words, when you talk about Fourier series, this must be a rectangle. We talk about a rectangle. Your data are inside a rectangle. Along x, finite interval. Along y, bounded function, bounded jumps. These are the prerequisites. This is essential. What is important but not essential is the function can be real or can be imaginary. It doesn't matter. We are going to work today with real, but it's not important. Work for both. And if the function is continuous or even smoother like differentiable, perfect, it works even better. So, as I mentioned before, you can choose different functions to expand your weird result, your function you want to expand in Fourier series. And today we are going to use trigonometrics, the original Fourier series, sine and cosine. So, the idea today is to expand any function fulfilling those requests defined on a bounded interval and continuous except a finite number of discontinuities, and expand it in sine-cosine trigonometric Fourier series. How it works? Let's work one example together. So first thing we are going to do is to choose the interval. So there's the real axis x, and I'm going to choose in principle a and b. And this is my interval for the Fourier series expansion. And of course, a does not coincide with b. A is strictly less than b, which means I have an interval, not just one point. For simplicity today, I'm going to choose, it's my choice, a symmetric interval. That's the 0 of the axis, this is x, and I'm going to choose it from minus p to p. As you can see, it's symmetric with respect to the axis. P, strictly positive number, anything. It can be 1, 2, pi, you name it. That's our choice. Any general situation of any general interval AB can be reduced to this one always by a transformation, but today let's focus on this symmetric interval. Once I have this P, I choose a function, f of x, and this function should be defined, if you remember, on this interval. It can be open and has real values. And this function is continuous on this interval, minus pp, except it's not necessary. Maybe a finite number of finite discontinuities. As you can see, it's easy to remember the word finite. Like the function in minus p, that's minus p along x-axis, this is 0, symmetric interval, y-axis for the function. The function can be continuous except some points where it's broken, jumps. At these points, the function is broken. But the jump of the function is finite. The function jumps from here to here, jumps from here to here, from here to here. The discontinuity is finite. As I said, you frame it in a rectangle. Then, from here, we have the function, we have the interval, we calculate the Fourier series. For this, I need to calculate 3 coefficients. So next step is the coefficients of the Fourier series, abbreviated. 3 coefficients. We need 3 types of coefficients. The first one is called A0, A0. The second one is a whole series of coefficients, AN. And the last one is another series of coefficients, BN. That's a traditional notation, historical notation. A0 is 1 over P. P is, remember, the semi-length of the interval, domain of definition. Integral from minus P to P, because you know your function only within minus pp, so normally you choose only this integral. You have no idea what data you have outside of this interval, and you integrate your function inside this interval. This is area of the function in this interval. Actually, that's the mean value of the function in this interval. This is A0. AN are very similar. 1 over P, integral from minus pp, f of x time cosine of n pi x over p dx. N is a label. We have an infinite number of such coefficients. Remember, we need to get to a series. So n goes from 1 to 2 all the way to infinity. That's a sequence of coefficients. Each of them is defined by the n, corresponding n, which comes here in the expression. X disappears. There is no more x here because x from here and here is integrated and disappears, is averaged. Pi is pi and p is the interval. As you can see, A are associated with the cosines, and B, to no surprise, they will be associated with the sines times sine of the same argument, dx, for the same range of n. 1, 2 to infinity. These are the coefficients. With these three coefficients, we build the Fourier series. The Fourier series is a function of x and is given by half of a naught plus the series itself, sum n running from 1 to infinity, parentheses, we have two terms inside, an, they are related to cosine, so just copy the cosine here, plus bn related to sine, so you copy your sine here. And that's it. This is your Fourier series. As you can see, it's infinite, it's a series, has a constant term up front, and runs from 1 because this constant term takes into account n0, so n equals 0 is actually here. And n0 doesn't make sense here because this term would be 0 and this will be 1, so you start on from 1 to infinity. If your function is continuous, on, of course, minus pp, we don't care about outside it, then the miracle is the function is identical to its Fourier series. They are the same thing. So here is my comment. Do not consider the Fourier series as a different thing, as a property of the function. The Fourier series is the function in all continuity points. Where the function is discontinuous, in those finite number of discontinuities, we have a little bit different formula. I'm going to show it immediately, but please remember this is essential, most essential. The function is its Fourier series. They are the same thing. Okay. What happens where the function is discontinuous? We have a very simple formula, a very natural one. If f is discontinuous at a point, let's say x naught, inside that interval, minus pp, then the Fourier series at that point gives you the mean value of the function inside the jump. Remember, the jump must be finite. So it's nothing but limit when x approaches the discontinuity point from the right, so I'm going to put a plus here, f of x, minus limit when x approaches the discontinuity point from the left, I'm going to put a minus, f of x over 2. The mean value of the jump is nothing but the jump at x naught divided by 2. Or if you want, f of x naught plus minus f of x naught minus over 2. In other words, if somewhere on the real axis between p and minus p, at the point x naught, the function has a jump, f of x is continuous up to here. This is its left value, f naught minus here. This is the right value of the function, the limit from the right, the limit from the left. This is a jump, it's finite. Well, the Fourier series will be here, in the middle. That's the value of the Fourier series at x naught. So basically, the Fourier series copies the function, it's identical to the function, follows the function all the way through continuity, stops here, jumps in the middle of the jump, and take it from here and follow again the function identically in the continuity range. The same thing. Fourier series is a function here. That's the whole thing. So the two formulas you need to know are just the function is identical to the Fourier series where the function is continuous, and this formula where the function is discontinuous. That's all. And I'm going to work a tricky example with you. So let's work an example. A tricky example. I'm going to show something you'll remember and use really funny. And for some reason, all the students have difficulty with this. Even if I explain it in a test, they have difficulty. So that's really a cool example. Let's work it together. I would say it's the most important example to understand how Fourier series work. So Very simple. P, let's put it pi. It cannot be simpler. So the interval is x belongs, remember, belongs, minus pi pi. Or simply you can write x is between minus pi pi. Perfect. The function I'm going to choose, f of x, will be sine of 2x. I'm going to choose a trigonometric function to expand in Fourier series. So the question is, for this problem, find the Fourier series of this configuration. This means find the three sets of coefficients. Remember, that's the procedure. Three sets of coefficients. The Fourier series coefficient. A naught, by definition, is 1 over p, that's 1 over pi, integral minus pp, that's minus pi pi, f of x dx, which means 1 over pi integral of sine of 2x dx from minus pi pi. This integral I'm going to solve really step by step, so I'm going to make a substitution. S is 2x, so ds is 2dx. I'm going to move very slow, so my integral becomes 1 over pi integral. When x is minus pi, s is minus 2 pi. When x is pi, upper limit, s is 2 pi. Sine of 2x becomes sine of s, and dx is ds over 2. So it results 1 over 2 pi. I got the pi, I got the 2. Integral of sine of s ds is negative cosine of s. Derivative of cosine is minus sine, with minus plus sine. Between these two limits, minus 2 pi, 2 pi. That's minus 1 over 2 pi. All the constants outside first, and then I have cosine in the upper limit, cosine of 2 pi, minus fundamental theorem of calculus, that's what we remember here, fundamental theorem of calculus, minus cosine in the lower limit, cosine of negative 2 pi. Cosine of 2 pi is 1. Cosine of negative pi, cosine is even function, it's equal to cosine of 2 pi, it's also 1. 1 minus 1, 0. Alright, a naught is 0. Next coefficient, an. An by definition is, remember what I wrote before, 1 over p, which is 1 over pi for my example, integral minus pp, integral minus pi pi, f of x, sine of 2x, cosine, a are the coefficients for cosine, cosine of n pi x over p pi dx. Pi simplifies out here, and then what I have here is a product of two trigonometric functions. The typical way, traditional way to solve this integral is to use trigonometric identities. Everything else is long and difficult. Trigonometric identities is the best way to solve it. So what I'm going to use today is product between sine cosine. I need to convert product of trigonometric functions into sum of trigonometric function. That will be easier to integrate. So I'm going to look up it. The formula I'm going to use is sine of some angle alpha times cosine of another angle beta. How much is this? If you Google it, you are going to obtain sine cosine is 1/2 parenthesis sine cosine sine of the sum plus sine of difference. Sine of the sum of the angles plus the sine of the difference of the angles. Of the angles. That's a trigonometric identity I'm going to use. Sine cosine converting to sine sine sum plus. Okay, so in my case, an becomes, last time I've seen it is 1 over pi, integral from minus pi pi, and then alpha and beta are 2x and nx respectively. So I'm going to have parentheses 1/2, which I can pull it here, outside it's a constant, sine of the sum of the arguments, 2x, one argument, plus nx, the other argument, plus sine of difference of the arguments, a difference between 2x and x, 2x minus x, because in this case 2x is alpha and x is beta is nx, close parenthesis, dx. Integrate, now it's simple, I have just a sine cosine, so the result is 1 over 2 pi, constant outside, parenthesis. Integral of sine is negative cosine, so it's negative cosine of 2x plus nx over the constant here, the coefficient of x, 2 plus n, between the limits, minus pi, plus, that would be minus cosine of 2x minus nx over the coefficient of the x, 2 minus n here, between same limits, minus pi, close parenthesis. What I use here is linearity of integral. Integral of a sum is the sum of these integrals, and then I'm using fundamental theorem of calculus, so my toolbox here uses trigonometric identities, specifically product into sum. You need this all the time when you work Fourier series. I'm using properties of integrals, namely today linearity, sum of integrals is integral of sum, and fundamental theorem of calculus to evaluate this result. I also want you to observe that 2x plus nx, the argument of cosine, is 2 plus n times x. So I consider it as a constant times x. Therefore, I have this constant here when integrate. Go back and check. When you differentiate cosine, you got minus sine. Minus disappears, you got sine. 2 plus n outside, sine of 2x plus nx divided by 2 plus n. Simplified is the sine. It's easy. Okay, so let's continue. An is 1 over 2 pi minus cosine of upper limit 2 pi plus n, x is pi, divided by 2 plus n, minus from the definition of the function, minus from the fundamental theorem of calculus, plus the function evaluated in the lower limit, cosine of negative 2 pi, negative n pi, divided by 2 plus n. We are done with the first difference, minus cosine in the upper limit, cosine of 2 pi minus n pi over 2 minus n, minus from the function in front of cosine, minus from the fundamental theorem of calculus in the lower limit, makes plus cosine in the lower limit minus 2 pi plus n pi, minus from here times minus pi plus n pi, divided by 2 minus n. Okay, let's calculate. I have the following situations. I have to calculate cosine of 2 pi plus n pi. This is cosine of 2 plus n pi. This is cosine of integer number, integer multiple of pi. Remember trigonometric circle. Cosine axis is x-axis. Multiples of pi are here and here. N pi, only here and here and here. So cosine is either plus 1 or minus 1 in multiple of n pi. Actually, it is minus 1 to the integer number power 2 plus n. That's it. If the multiple is even, you are going to end up here to the right, like 0, 2, 4, or 0, minus 2, minus 4. So for even multiple of pi, the cosine is plus 1. Indeed, minus 1 to the power even is plus 1. If 2 plus n is even. While when 2 plus n is odd, you are going to be here always like pi, 3 pi, 5 pi, or minus pi, minus 3 pi. And you have minus 1. So if 2 plus n is odd, you have minus 1 to an odd number is minus 1 as it should be. So it's minus 1 if 2 plus n is odd. You can use this curly bracket, these cases, or just this expression is the same thing. I prefer this, is way simpler and easy to write. Okay, so following all these situations, we have an is 1 over 2 pi, and let's simplify a lot. I have minus cosine of, let me bring it here, cosine of 2 pi plus n pi is minus 1 to the power 2 plus n divided by 2 plus n plus minus 1 to the power minus 2 minus n, the coefficient here of pi, minus 2 minus n. It goes simple. Over 2 plus n minus minus 1 to the power 2 minus n, 2 minus n over 2 minus n plus coefficient of pi here is minus 2 plus n, so minus 1 to the power minus 2 plus n over 2 minus n. We are done. Okay, and now please check this. Minus 1 to the power minus 2 minus n is nothing but 1 over minus 1 to the power 2 plus n. And this minus 1 to a given power can be plus or minus only. It depends on the parity of 2 plus n, if 2 plus n is even or odd. So actually 1 over minus 1 to 2 plus n has the same values as minus 1 to 2 plus n. This is equal to minus 1 2 plus n. Please check this by yourself, it's always true. So actually very important, it doesn't matter if your minus 1 to integer power is in denominator or numerator, they are equal. Same thing. So I have the same denominator here in these two fractions. I have the same powers here, minus 1 to plus n, or 1 over minus 1 to 2 plus n, minus plus, they reduce. And the same thing happened here, same denominator, minus plus, minus 1 to 2 minus n, minus 1 minus 2 plus n, but minus 2 plus n is 1 over minus 1 to 2 minus n. Same signature, same cases, plus minus. They go synchronized, same things, they are the same thing. Minus plus, they reduce, result is 0. And the last set of coefficients Bn, they are 1 over p pi integral minus pi pi my function sine of 2x, and then sine components n pi x over p pi dx. And following the same procedure, remember, you transform the product into a sum, and then you integrate each of the integrals, you obtain the fundamental theorem of calculus formula, you calculate. If you do it by yourself, you are going to have 0. So the result, apparently, the Fourier series, which is a0 over 2 plus sum n from 1 to infinity an cosines n pi x over pi plus bn sines sine of n pi x over pi is actually a0 was 0, an is 0, bn is 0, is 0. And here I have a big contradiction. Problem. We call it paradox. Because on one hand, the function sine of 2x is continuous. Of course, it's elementary function, it's continuous, all over real axis, including minus pi pi. So the Fourier series should be identical to the function. But the Fourier series end up to be 0. And sine of 2x is not identical to 0 on minus pi pi. So we have a problem here. Let's detect it. Where did we make the error? Let's go back. And here, one page back, the result is very simple. Look again at this formula, the calculation of an. The first two fractions are okay, because denominator is 2 plus n, and n, remember, can be 1, 2, 3, all the way to infinity. So 2 plus n is never 0. This formula exists, they are exact numbers. But I have a problem with the last two. The last two functions have a denominator 2 minus n. And actually it happens when n is 2 inside the series, this denominator becomes 0, and then I have division by 0, which is forbidden. So this formula does not work for n equals 2. How do you remember this? How do you know this? Well, I want you to develop the magic eye. And that's the goal of this little exercise. Please develop the mathematical magic eye. Whenever you build formulas, you calculate formulas, and you have expression over expression, always check the denominator is never 0. This is when your calculations are valid. Develop this mathematical magic eye and have always an eye on the denominator. Like when you drive, you look into the rear view mirror from time to time, you always check your denominator, the one you obtain, never be 0. Develop this instinct if you want to be successful in applied math. And this instinct tells me I have the denominator, they come up from my integration. Cosine of ax integrated is sine of ax over a. That's how they come up. I have new elements here, so check if they are 0. And yes, I have situations when they are 0. So I have to deal with this. We have to study it in particular. So the procedure is this. If denominators are 0, study this situation independently, separate. So in my case, I'm going to do this. Coming back to the coefficients, an, the definition was 1 over pi integral minus pi f of x sine of 2x cosine of n pi x over pi dx. Pi simplify, and it is. The previous result was 0 if n is never 2. Because when n is 2, I cannot calculate it. I have division by 0. So that formula is not valid for n is 2. For n equals 2, I have to calculate it by itself. So let's calculate a2. When n is 2, a2 in particular independently is 1 over pi integral minus pi sine of 2x cosine of 2x dx. I'm going to use another trigonometric identity here, namely sine of alpha cosine of alpha is 1/2 sine of 2 alpha, the double angle. So actually sine of 2x cosine of 2x is 1 over 2, so I have 1 over 2 pi, constants outside, integral minus pi, sine of double, sine of 4x dx. And what's the result? Over minus pi, sine of x is periodic, it's a full period. 4x is faster, 4 times higher frequency. So oscillates 4 times more, has 4 full periods between minus pi. Each such period results in 0 integral, 0 area. So you have 4 times 0, this is still 0. But it's a correct 0, it's not 0 divided by 0. It's when students always get stuck. They have 0 over 2 minus 2, 0. We don't know what it is. So if you break it down in the general formula and the exception when n is 2, I found 0. That's true, but now it's correct. So I can say an are all 0. That's correct. Last step, bn's. Now it's simpler because we know what may happen. The coefficients bn are given by the formula 1 over pi integral minus pi sine of 2x, our function, sine of n pi x over n by the book, formula over pi, pi simplifies out, and then I have sine. I have to use again trigonometric identities. So using trigonometric identities, let's look into the formula. I have the situation sine of alpha, sine of beta. So I have a product sine. The product sine is given in the formulas 1/2. I'm going to look at it. Sine is cosine of difference minus cosine of sum. cosine of difference, alpha minus beta, minus cosine of sum, alpha plus beta. That's the formula. You can Google it, get Wikipedia, 4 screens, scroll down, you find these identities from product to sum. Therefore, Bn is 1 over pi, 1 over 2 makes 1 over 2 pi, constants outside, integral minus pi pi, cosine of difference, 2x minus nx, 2x minus nx, minus cosine of sum, 2x plus nx. Integrate. So we have 1 over 2 pi common factor, and then cosine integrated is sine of, and I'm going to pull x common factor, we learn this, is 2 minus n x over the coefficient of x, 2 minus n, between minus pi and pi, minus, again, sine, in this case I have 2 plus n times x over 2 plus n between minus pi and pi equals, and now the mathematical magic denominators, you see this formula, no denominators, no denominators. Oh, I have new denominators, check if they may be 0. This is never 0, because n is only 1, 2, 3 positive integers, and 2 plus positive is never 0, but 2 minus n can be. So here I have a caveat, so I'm going to expand this in cases. That's the procedure always. So Bn is 1 over 2 pi cases, curly bracket. Is this situation if denominator is never 0, so it's sine of 2 minus nx over 2 minus n between minus pi and pi. If n is not 2, and if n is 2, I have to start it from the very beginning. It is the original formula, b2. So I have 1 over 2 pi, and then let's calculate this finite difference. I have sine of 2 minus n times pi over 2 minus n minus fundamental theorem of calculus, sine of 2 minus n minus pi over 2 minus n if n is not 2. And here let's calculate it from the formula, is 1 over pi integral minus pi pi sine of 2x, and n is 2 in this case, so it's sine of 2, that's n, x, pi simplified out, dx. Next step, Bn r, 1 over 2 pi, curly bracket. Let's look together. I have sine of integer multiple of pi. N is integer, 2 minus n therefore is integer. Integer multiple of pi, sine is 0. Trigonometric circle. Sine axis is a vertical one. At multiples of pi, integer multiple of pi here and here, sine is 0. So this is 0 when n is never 2. So for all the terms n not 2, Bn are 0. What happens when n is 2? Let's calculate. I have 1 over pi, and then I have sine of 2x, sine of 2x. This is sine squared. Square of 2x dx when n is 2. I can go ahead and just write b2, because the rest of bn's are 0. I'm not going to carry this with me anymore. Just b2 is important. And actually I took into account here 1 over pi. So I'm going to correct this 2 pi here. So it's going to be 1 over 2 pi integral from minus pi pi sine square. I'm going to use a trigonometric identity again, namely sine of half angle alpha over 2 is plus minus square root of 1 minus cosine square of alpha over 2. I'm going to square it. So I have sine square is 1 minus cosine of double 4x over 2 dx. And that's 1 over 2 pi integral of dx over 2 minus pi pi minus 1 over 4 pi integral minus pi pi cosine of 4x dx. Second integral is 0. Remember why? Trigonometric integral periodic function between a full period. 4x has 4 periods between minus 5 pi, so it's 0. And what is left is 1 over 2 pi times 2 pi over 2 is 1 over 2. So in the end, the Fourier series is a0 over 2 plus sum n from 1 to infinity an cosine of n pi x over 2 plus bn sine of n pi x over 2. Let's not forget here the 2. Here it's a little error. This is 2 times because 1 over 2 pi was from the general formula. So actually this is twice. And everything here is twice. So I have a 2 here and a 2 here. Actually the result here is 1. Please double check yourself. So a0 is 0, all an are 0, and the only bn is 0 if n is not 2. So what is left over from the Fourier series, all the terms drop to 0 except the term number 2. So it's b2 sine of n pi x over pi over pi. N is 2 for this term, so it's b2 sine of 2x, and b2 is 1, so it's sine of 2x. So what did I get? I get f of x sine of 2x given to us is its Fourier series because it's continuous, so it's identical to Fourier series, which is sine of 2x. It's one of those, like in one of those puzzles where you work a lot and obtain 1 equals 1 or 0 equals 0. No. The goal of this example is to show you that the Fourier series is the function. It is the function and nothing else. So what you have to do, once you are given the function, like in my case sine of 2x, just check the arguments of the Fourier series. Remember the arguments of the sine cosine n pi x over p. Only look at this. In our case it's n pi x over pi, so it's nx. Look at the argument of your function, the given function. Look at the argument of your Fourier series and ask yourself, is there some n such that these two arguments coincide? Of course it is. If n is 2, they coincide. So no need to calculate, no work. The Fourier series is a function, end of story. This function is already expanded in Fourier series as a result. A trigonometric function, it's a trigonometric function, is its own Fourier series, which makes this situation way simpler. Well, thank you very much for your attention, and now I'm going to move to the computer and show you very quickly how this works. I'm going to choose a certain example, and I'm going to use a computational algebra or a symbolic calculation program to calculate the Fourier coefficients in general for a given function. You can use Mathematica, Wolfram, or MATLAB, or any symbolic program, Python, you name it. And I'm going to show you on the computer how simple it is. Thank you very much for your attention. Thanks for watching. I hope you like the content, and please leave any questions or comments in the section below. If you learned something today, then please hit the like button and support my channel by clicking the subscribe button below. Thank you very much. Have a nice day.